Thank you. So huge pleasure to give a tutorial at the school. Yeah, indeed, I missed the first information theory school. I think that was not very well advertised. And so the second and the third one I did attend. And in fact, okay, I mean, some of you, I'm sure, here for the tutorials and to listen to all of the smart things we can say to you. But to me, the best memories are the people I met. And actually, some of my strongest collaborations were formed in those two events when I, was meeting young students from all across the world who were interested in similar topics. So, and actually, so when I was preparing for this, I distinctly remember how we were very mean students, right? We would sit in the back, and then we would comment on lectures, right? And I remember we invented the metric, how many proofs a lecturer does, right? So that would be our, okay, so how many proofs per tutorial, and that would be our quality scale. And back then, I thought this was a very smart thing, right? Okay, this guy's good, right? He gave us many proofs. This guy's bad. He didn't give us any proofs. And now, so when I was preparing for this, I think I became either older or wiser or maybe better teacher. So there is not too many proofs in here. And why? It's because, I don't know. So I personally learn by studying myself. So when somebody presents a proof, the most important thing for me is the motivation, why I need to learn it. So, and if I'm motivated, then I can go back and really understand it. So for this reason, most of the talk I will try to motivate the interesting new questions which me and my group are studying. And for that, let me start with the following slide. So how does your cell phone work? We are all very used to these little gadgets in our hands, right? So we know, I'm sure most of you know that the cell phone, connects to base station. There's this network of base stations, right? And as you go around the United States or the world, right, you connect to different base stations. Okay, but what probably not too many of you know is how does actually, how does the base station know when to allow somebody to send something, right? How do so many cell phones together send stuff to the same little small base station in here? Okay, so what happens is the following. So when you power on your cell phone, first of all, there's a special frequency band or special channel in the LTE speak, right, where the newborn devices announce their presence. Now, the key idea here is that since there are not too many devices being born per second, right? Okay, there are exceptions, like a train leaving a subway station or entering a subway station, but let's leave it aside, right? So most of the time, cell phones do not get born, right, with huge rate. So there are very few, very low traffic on this channel, right? Okay, so now once your cell phone manages to announce its presence to the base station, and as I said, the main assumption here is that there are no collisions because there are not too many cell phones. Okay, so after that, base station says, okay, I got it. Now I'm in control. You stay completely silent until I tell you to speak. So this is how cellular network works, right? It's completely what is called orthogonalized, right? So whenever your cell phone speaks, and it wasn't like that all the time. At some point, Qualcomm, okay, I shouldn't say that because this is recorded. I hate this, so I cannot be honest with you. But okay, so at some point there was technology called CDMA, right, which was supposed to do it the opposite. But in the end, orthogonalization won. So all the current standards are based on orthogonalization. Okay, so you could say, all right, and that's what the question many of my students and actually my family also, they ask me, Yury, everything works. Why do you have to do this, right? Why do you have to keep studying? This question. Okay, so now there is an interesting, of course you could say, like when you hear this commercials, right, they tell you, you want your cell phone to download more and faster, but that's not the only reason actually. There is a fundamental shift nowadays happening in how communication will work, and that's why I think it's an interesting and very timely opportunity. Okay, so what's this new thing? This new thing is what's called Internet of Things. Right, so there's all sorts of this funny applications where we really want to track lots of distributed objects. Right, we want to know where our car is, where our cow is, since we're in Texas, right, where my dog is, and so on, and what it's doing. So what's the temperature of the body, and so on. So we want all the sensors to constantly send data, right, to us and maybe to central locations in agriculture and so on. Okay, so there are different estimates of people called futurists. I don't know what this profession is, but they sort of try to predict stuff in the future. So they predict that we will have around 100 to 500 devices per household, right, eventually. I don't know what eventually is, but okay, let's take it for granted. So currently we have about 1, or maybe, okay, order 1, right? Then we will have order 100. Okay, now there's no shortage of standards who claim to solve this problem, right? Meaning the problem is you have many sensors, they all want to send stuff, right? And they're very low power. So I spend a lot of time studying the standards, and the summary is they don't do the right thing. So, and the reason is because there's no theory behind it. So all of this is just repurposing of some old ideas, orthogonalization, you know, Aloha, CDMA, and so on, which I will tell you about this old technologies in this tutorial. Yeah, so this is important to remember. Okay, so let me also tell you that fundamentally there are 2 mindsets here, right? So how are we going to have these quadrillion sensors send stuff, right? So there's one idea which is called low power WAN, low power world area network, which says, okay, what we will do is we will have a few base stations per city, for example. And then these base stations will service very long range connections, right? This is going to be sub-gigahertz communications which happen on a very long range, so on the city scale, right? So essentially one base station, one tower will collect information from something like entire College Station city or Boston or something. Okay, there is another mindset which says, no, the Internet of Things will develop exactly like cellular network, which is we will cover the Earth with, you know, with base stations every 100 meters, and this is how the communication will work. Now, okay, so I mean, again, it's about predicting future, right? This is very far into the future, right? So I'm mostly mentally focused on this picture. And also there's some commercial reasons, like in the United States, it's very expensive to maintain a tower. So, you know, it's not likely that the number of towers will increase significantly. Okay, so basically we are in this situation in my mind. Okay, so, all right, so another question I frequently encounter when I talk to my colleagues in the electrical engineering and computer science department, right? So many of them do other things, and they say, Yury, what's the point? I mean, do we have to really focus on communications in this IoT? Because, you know, IoT is a buzzword, right? Not as strong as deep learning, but it's a buzzword too. And when I talk to my colleagues, right, some of them say, okay, what is IoT? They say, oh, IoT is gallium arsenide substrate because it will reduce the drain. Some others say, oh, no, it's the database backend, right? Because you need distributed database. So IoT is a different thing for different people. So I want to claim that IoT is all about power consumption of communication. So let me argue this a little bit, right? So if you look at the typical sensor, right? I mean, this is the cheap Arduino. Right? You can buy it, embedded controller, right? So this is the Zigbee, one of the popular radio solutions. Right, so okay, so when they are asleep, meaning they only monitor some kind of wake-up event, right? They consume about 1 microamp. So this is LP1 from one company I was consulting for. So okay, so this is a number, right? So when they are asleep, they all consume about 1 to 5 microamps, right? Okay, so once you wake up CPU, oh, and by the way, yeah, the silicon people, right? They will tell you that IoT is all about reducing this, right? I'm going to sell you better CPU, maybe multi-core something, right? I will reduce this consumption, right? So it's about 50 microamps, right? When you wake up the CPU. So what do you think happens when you power on the radio transmitter? So the radio transmitter for this, I mean, Zigbee is essentially in one house. This is not long-range communication. This is inside one house. It's a very short-range solution. So it consumes about 40 milliamps, right? So this is an order of magnitude, right? So now what I'm trying to say here is that in my talk, right, and in my research, I'm trying to minimize this number by a factor, right? I mean, other people try to minimize this number by a factor. So now I hope you understand, right, why it's important. Okay, so now you can do some calculation. This is another smart thing I learned from IoT folks that I mean, we used to present everything in dBs and milliamps, right? This doesn't resonate with people, right? What resonates with people is how many years you get per AA battery, right? Because, I mean, communication guy would say, oh, my protocol reduces energy consumption by 3 dB. And people would say, okay, what? No, nowadays you say it reduces, the battery goes from 10 years to 20 years, right? And this somehow is much more impressive than 3 dB, right? So, and that's exactly, yeah, essentially all the consumption is here for the sensors. Okay, right, now these numbers, when these guys measure X, right, Zigbee, for example, they say, okay, 40 milliamps, this gives you reliable transmission in the absence of interference, right? Now imagine a situation, right? We are currently at essentially 0 density of nodes, right? But this is projected to grow 100-fold, right? So, okay, so once everybody starts shouting all those sensors, right? Of course, these numbers will go up, but the question is how much, right? And this is what I think information theory can help with, right? Because technology people, they would say, okay, Qualcomm says, let me simulate my system and I'll tell you, right? But I mean, by the time those batteries in 10 years start to run out, right, the protocols might be different. So that's what I want to argue. That we as information theory community should provide benchmarks for this kind of information theory on a city scale, right? Okay, so let's try to understand what kind of problems we'll face. Yes, question?
On the 40 and 20 milliampere numbers, are they operating on the same frequency, similar frequency band?
Okay, the question is for Zigbee versus LP1 sensor. No, of course not. This is 2.4 gigahertz, and this provides higher rate. This sensor only sends 100 bytes, and for 10 to 20 kilometers, but it's on sub-gigahertz.
Might that be the reason why it's transmitting at a higher power, because it doesn't have sufficient range?
Oh, sorry, that's probably Qualcomm. Yury, you're disclosing our secrets. Okay, sorry. Apologies. Yeah. Sorry, Rajesh. So what's
Since it's operating in a band where the coverage is not all that high, 2.4 gigahertz, might that be the reason why the transmit power is higher?
Oh, this number, you mean by factor of 2? Oh, this, I mean, okay, this is not very optimized for low power. I mean, really, these numbers, by the way, how these were obtained, I don't remember, right? So I measured this, I don't know, a year ago. So yeah, yeah, I mean, order of magnitude, I can vouch for this, but, coefficient 2, let's not, yeah. Okay. Right, so here's the envisioned solution, right, which is in my mind, and in your mind, should be throughout this talk, right? So what we will do is, we have these sensors, extremely low power, right? Even though CPUs don't consume that much, you still want them to stay asleep most of the time, right? So the sensor, really IoT guys, they want a solution like this, right? My sensor is asleep all the time, right? It wakes up periodically, maybe when it's capacitor charged from the solar battery or something, right? It wakes up, has very short time frame. It cannot acquire the paging channel, wait for LTE base station to tell me when to speak, right? He wakes up, his data, he blasts the data out in the air and goes back to sleep, right? There is no axe. I cannot wait. I cannot check if my message was delivered or not, right? So this is the solution. I really want the coding to be done in such a way that I blast my coded packet. It collides with 100 or 1,000 or 10,000 of other packets, right? And base station still able to decode it. So this is what I want, right? Okay, so let's see if we can do this, right? So throughout the talk, as I said, we are interested in low energy. I'm not interested in particular, how does turbo code or LDPC code or polar code behave, or what it achieves. I'm interested in fundamental limits. However, it's a fallacy to just say, okay, let's just assume unbounded computation, right? So I will also try to do some kind of low complexity solutions, meaning my building block, I assume that I have a black box which is able to decode single user code, right? So that's what I call low complexity. I mean, you could still say it's very high complexity, but notice that decoding is done on the base station, by the way. So base station can definitely afford decoding single user codes. Okay, so now in this process, what we need to do is we need to understand several aspects. And my original plan when I started preparing this tutorial was to cover all of this. Now I will probably skip one for most of the part. Okay, so let me first explain what the issues are. So now in IoT, you don't send streams, right? You send 100 bytes, 100 bits actually, right? Because it's like parking update. My spot is empty or occupied, right? Okay, so the packets are very short. The data packets are very short. Now there is an issue of multiple access. So I figured out, and Krishna said that my hunch was correct, that not too many of information theorists nowadays know all the results about classical MAC, so I will spend some time talking about results in the classical multiple access. Right, then I will talk a little bit about what's called low complexity MAC. How do you achieve, how people were thinking about achieving those limits for the Gaussian channel. And finally, so this is really the new part. But as I said, I wouldn't be very upset if I don't get to there, except for just flashing some results, because I really want to convince you that this is cool stuff happening, right? And then you can learn it yourself. Okay. Right, so one line summary of my talk is that what I learned is that it's immensely harder problem to support 1 million users sending in 10 bits per second than to support 10 users sending at 1 megabit per second, right? It's just, I mean, it's just a much harder problem, and we have no idea how to solve this, despite many protocols claiming to do that. Okay, so this you just have to trust me, right? So this is the summary of my thinking after several years. Okay, so let's start. So the question is, can we quantify this? So I think you're talking about quantifying the word easier. No, I cannot. That's just a hunch. Okay, so let's talk about a little bit of background on finite block length information theory. Okay, so let's do the following case study. Consider a binary symmetric channel, block length 1000, flip probability 0.11. By the way, is there a clock here anywhere? Can I? Because I shut down my cell phone, so now I cannot check time. Okay, yeah, I can see it. Yeah, good. Okay, so right, so let's suppose. So I ask you, right? So I give you 1,000 channel users of a binary symmetric channel with capacity 1/2, right? And I ask you, okay, so how many bits can you transmit with probability of error 10 to the minus 3, right? The answer is a number, right? Okay, so between 0 and infinity, right? Okay, so let's first try to do repetition code, right? So if you take 47 bits and repeat it 21 times, right? So then you can calculate that you do achieve probability of error less than 10 to the minus 3, right? Okay, so this is pre-Shannon sort of situation, right? If you do read-Muller code, right? The best read-Muller code that fits 1,000 block length, right? Is this 47, 64, sorry. And then you can use it several times, right? And send 112 bits. Okay, so this is what you can, right? So Shannon's prediction, Shannon says, okay, capacity of this channel is 0.5 bit, right? Per channel use, you have 1,000 channel use, so you have to be able to send 500 bits, right? So what's the actual answer? What do you think? What's your guess? Krishna, what's your guess? I put it, yeah. That's why he will never invite me again. Huh? Okay, that's very pessimistic. So he is a coding theorist. Yeah, so the answer is this. So yeah, that's a little bit better, yeah. Actually, I said pessimistic. I think he was actually optimistic. He thought read-Muller codes are good.
No, it's better than the
Yeah.
voice is better.
Yeah, anyways, yeah. But yeah, so it's actually, yeah, it's a little bit closer than, so. But the interesting thing here is that, okay, there are two things. I do this experiment for many years, right? And nobody ever, I mean, even classical, like I asked Tom Cover this, and then he didn't guess even closely. He also thought it would be a lot smaller. Actually, no, he thought it would be a lot closer. Yes, he thought it's going to be 499 or something. So yeah, so nobody guesses this, right? So the finite block length information theory, right? So all of these people who, like myself, right, who work on this, right, we try to get these numbers, right? So notice that the problem here is that this is a very hard optimization problem, right, over all possible block codes, right? So how on earth can we bound it so well, right? So I mean, this is the art, right? So how do you come up with good bounds and so on? Okay, so I don't have much time to discuss this, but I wanted to plant the following mental picture in your head. Okay, so here's noisy channel, right? So how do you send data over the noisy channel? Well, Shannon tells us you put data bits, you add redundancy, right? When they pass through the noisy channel, you can use redundancy to decode the bits, right? Okay, so now in the world of probability of error and rate, there is two phases, right? If you are very greedy, you want low probability of error and very high rate, this is not possible, right? This is the world of impossible. This is the world of possible. And then there's some boundary separating this. So we, as information theorists, are number one, the career statement, the mission statement is to study this boundary, right? We're studying fundamental limits. So now the interesting thing that Shannon observed is that as block length evolves, as block length increases, right, this boundary becomes very steep, right? It becomes a step function. The phase transition happens at exactly at a well-defined number, which is capacity, right? Okay, so this is the Shannon kind of thinking, right? So this is the 1/2 situation, right? And what we are interested in is an understanding for a given n, for a given block length, how does this shape look like? Well, it turns out that this shape is very much Gaussian CDF of width, which is square root v over n, and this parameter v is what we call channel dispersion, right? So the hard problem in finite block length information theory is getting those two numbers, 414 and 416. The easier number is to at least get this next order asymptotic term, right? So okay, so that's right. So that's the estimate, right? And then of course you can answer questions like what's the typical block length you need to achieve fraction of capacity and so on. Okay, so right. So then we get this evolution of these curves, right? So we have to describe evolution of this boundary, right? And then historically there were two ways how you would think about describing this evolution. One is the vertical asymptotics, right? You fix a rate, and you ask how quickly does the intersection point go to 0. This is called error exponent, right? And then the other one is horizontal asymptotics, which is fixed probability of error epsilon, and then study the speed of convergence here. So there were classical results on this from, I think, 70s, and before 70s, this essentially was understood. Okay, so now what did the new century added? Well, we now know that that horizontal asymptotics provides a lot better approximations in the engineeringly relevant regimes. So we study new channels and so on. So this is a quick summary of finite block length information theory. Right. So the important quantity here is this number r star n comma epsilon, which is the maximal achievable rate for a given block length n and a given probability of error epsilon. Right, so this point drifts towards capacity, and we want to describe the speed of this convergence and so on. Yeah, so again, I mean, to summarize, right, half a century of research, I mean, roughly speaking, for ergodic channels, you always get this kind of estimate. Right, you get capacity minus square root v over n times some Gaussian quantile, right, at epsilon. Okay, so now. For future, right? So what we need to understand is also how do the proofs go? Okay, so the proofs go as follows. So we have to prove upper and lower bounds, right? So what you do is you take this, right? So py given x is a channel, right? And you select some kind of auxiliary output distribution, right? And you take this this quantity, log likelihood, right? And you say. And there are special tools which allow you to conclude that r star of an epsilon is upper bounded by epsilon quantile of any such quantity, right? And then the job is to optimize over qy so that this quantile is minimal, right? Then you get the best converse. And similarly, for the achievability bounds, you can prove that it's also lower bounded by epsilon quantile of this. So here you're supremizing over qy. There is some kind of minimax saddle point equation, and then that's why these two numbers are essentially equal. Okay, so now, right, another important player in our discussion will be, this log likelihood ratio, right, is what we call information density. So when I talk about achievability bounds for multiple access channel, I will use this quantity. The important thing to remember is that this is a sum of IID, right? So this information density, log likelihood, right, is a product, so it becomes a sum of IID random variables. So sums of IID behave central limit like, right, CLT like. So that's why you get all of this Gaussian CDFs. Okay, right. So this is the mental picture, right? Fundamental limit, right? And then information theory tools allow you to describe that fundamental limit using quantiles or distribution of a quantity called information density, right? Which is very, very central limit like, right? So information theory provides connection between operational quantity and this probabilistic object, right? And then probability tells you how this behaves. Okay, so this is the good mental picture. right, another nice analogy is the following. So Shannon told us that each channel is a bit pipe, right? And the width of this bit pipe is capacity, right? So if you stuff data into the channel, only the capacity passes through, right? So this is the mental picture. Now for finite block net, what happens is there is some fluctuation of this pipe, right? Where fluctuation of the width is square root v over n, right? So when you try to push the data in, right, depending on the realization of the pipe, on the jittery, on the width of the pipe at instantaneous, right? That's where you get probability of error. Okay. All right. So I think, right, as I suspected, I don't have time to cover. I wanted to show you at least 2 proofs for the finite block length part, but let me skip this. Also, it makes me sad because this is a slide which would celebrate its 10th anniversary. So I don't have, I can't, yeah, I showed it in my first ISIT. So that's, and by the way, here's one promise. I didn't want to say it in the beginning of the talk, especially because it's going to be published, right? But I say it now. So if you watched up until here and you're actually interested in any of the multiple access stuff and you email me, I promise I will respond. So this is my pledge. Okay, okay. Including questions about this. So let me skip all of this. Let me skip the tricks how we prove converses. Nice pictures of Renier, Kullback, and Leibler, and very hard to find pictures of those 2 gentlemen, Neyman and Pearson. Yeah, anyways. So, okay. Right, so let me skip all of this. Except for one thing. Right, so for the Gaussians, we will study Gaussian channels a lot in this talk further on. Now, one important thing for Gaussian channel is that this dispersion is given by this formula, right? So the capacity, of course, you know, 1/2 log 1 plus p, right? What's the fluctuation size? The fluctuation size is given by this formula. Now, this is the amazing property of the Gaussian channels, that the variance is self-bounding. So when power grows, the variance doesn't explode. Okay, so so this v of p is always upper bounded by a number. Okay, so that's very important. So what this means is that whenever you calculate capacities in Gaussian channels, regardless of the SNR, you can take limits of SNR and so on. The correction term, the finite block length penalty, right? The stuff that you subtract from 500 bits to get 414, right? This stuff is uniformly bounded in power. So that's a good thing to remember, right? So for this reason, so if you just argue from capacity and subtract capital O of 1 over square root n, you're never wrong in Gaussian channels. That's a good thing to remember.
It seems like it's good news or bad news depending on the regime where you're interested in, right? If you're looking at the high SNR regime, that seems like it's a good thing because it's an additive gap and the gap is bounded. But if my SNR is very low, then it becomes a really bad.
Fantastic observation, Krishna. Yes, indeed, and that's one reason why it took a lot longer to achieve capacity in the JPL setting, right, which is far deep space, right? There you needed turbo codes, right? Whereas on the landline you could get away with simpler constructions, right, like trellis-coded modulation. You are absolutely right. Yes. So coding for low SNR channel is much harder. This will be an important point later as well. Yes, but right. Okay, so let's talk a little bit about classical multiple access channel. Okay, so this is the situation, right? We have noisy medium, several transmitters, all of them try to send to the receiver. So this could be, I mean, in our minds, everything is a cellular network in my mind, right? But when I show this picture in my department, Bob Gallagher's initial reaction is, of course, it's a satellite network, right? So anyway, so that's because, yeah, so they worked a lot on optimizing satellite networks. So, okay, so networks could be different, right? So, okay, so here's the networking folks thinking. They think of this network as essentially a collision channel, right? They say, okay, so there's this noisy medium. I put my packet there, right? It travels there, right? If somebody puts something on top of it, right, then both packets die, a painful death, right? So, okay. So, and then the question in networking is how do you arrange transmissions in such a way that packets don't die, right? That don't collide too much, right? Okay, so I mean the typical result there is that, you know, if you do aloha, meaning random placement with slots, right, slotted aloha, then you achieve something like, right, so the utilization, meaning the fraction of channel time, which when it carries an uncollided packet, that's a useful fraction, right, is about 37%, right? I mean, you could think of this as a good thing or a bad thing, but yeah, initially it was a good thing. Okay, so one thing I like to, throughout the talk, I'll try to state some open problems. This is a famous open problem, which I have never heard about until I started studying multiple access better. So the question is, how large can this number be? Turns out it's an open question. There was many works, and people were pushing the bounds, and as maybe usual in this case, right, the Russians pushed it more sort of right, with more force. So, but the initial ideas are due to Gallagher and his students Kapetanakis, because initially people thought that you cannot beat this 0.37, and then he showed that actually you can. And after that, people started studying, okay, what's the best? So I think the bounds are progressively shrinking towards half. So there is a sort of unspoken conjecture. Maybe it's a half. But yeah, so again, if you're interested, email me. I'll tell you exact statement. This is called, sum rate capacity of the collision channel with ternary feedback. That's the technical term. Okay, so right, so what I like to say in my lectures at MIT, I say that, okay, so networking people try to achieve capacity, right? Try to push, not 37%. We in information theory, we want to achieve beyond capacity, right? We don't want to achieve capacity, we want much larger, right? And of course, initial people say, I don't understand, this beat pipe, right? How can you push through more? Well, because, right, we can push more because there are many more of us, right? Each one of us is power limited, but all together we can send, right, with much higher power, right? So that's why by exploiting the physics of collision, right? So networking attitude is that collision just destroys information, right? We could say, no, let's look carefully, right, inside the collision. Maybe we can extract some information from the collision and not just erase all the picture. Okay, so how is this possible, right? So let's try to see what's the math here. All right, so here's the formalism. I'm sure you all seen these definitions of encoders, decoders, and probability of errors, right? So let me just to be on the same page, right? So we have a memoryless channel with two inputs, right? Every channel use two guys. Each sends one input, right? The channel takes those inputs, scratches its head, adds some noise, and produces some output, right? So that's the game. And now the goal of this game is for the two guys to send one of the 2 to the nr1 messages for one guy and 2 to the nr2 messages for the other guy, right? Okay, so this is our job. So okay. And what's important is, right, so the decoder sees the channel outputs and produces the estimates for both messages. And the classical definition of probability of error is this one. Meaning, so my decoder should be able to decode both messages with probability greater than 1 minus epsilon. I want to stress this fact because one of the innovations of the sort of thinking about 5G information theoretically is that this is the wrong definition of probability of error. We'll talk about it later. But for now, just remember that all of the classical results in Cover and Thomas and Chizer and Kerner, they are for this probability of error. Okay. Right, so what's the, right, so how do you define finite block and fundamental limit? Well, similarly to before, right, we just say, okay, fix n, fix epsilon, and ask for all possible pairs, R1, R2, for which codes exist, right? So it's some collection of discrete points for each n. Now you're interested in, right, in sort of taking the convex closure of the sets, right? So you take convex how, right, and then closure. Okay, so on the right, so this region, and then you take epsilon to 0, right? So you want a vanishing probability of error, right? Yeah, for the capacity region and for epsilon capacity region, you don't take epsilon to 0, right? Okay, so with this definition, what's the famous result due to Alsvede and Liao for this? Now, C and Dueck proved the strong converse, so that now we know that also. For C sub epsilon. Okay, so how do you compute this? Well, you just take convex how of the union of these pentagons. So what is a pentagon? Okay, pentagon is a two-dimensional region, right? Parameterized by two input distributions, right? So you fix two input distributions. You compute these three numbers: mutual information, joint mutual information conditioned on one user, mutual information conditioned on another user. Put these three constraints, get some kind of nice convex region. I forgot to say greater than 0, right? All rates are greater than 0. Take their union, convex Hall closure. That's the answer. A beautiful theorem. OK. Right, so there's an interesting thing here. So that when you take convex Hall, right, so we're all used to this idea that convex Hall corresponds to time sharing, right? Now, if you're so this is a multiple access channel where users are perfectly synchronized, right? At the sound of the fire pistol, we both start transmitting our blocks, right? Now, of course, in many cases, you want to also, especially in satellite, right? You want to study the question when there is no firing pistol, right? So the frames are not synchronized. So without synchronization, the answer is the same, except you don't take convex Hall. So that's another interesting result. More recent than Alsved and Liao. I don't remember who it's due to. OK, so right. So now, OK, again, so if your channel has cost constraints, then you cannot do this. You have to introduce time sharing variable. OK, so that's another caveat. OK, so right. Yeah. So this is the picture how these pentagons look like, right? So this is the mutual information. I mean, the intuition here is this is the rate at which R2 can transmit if x1 was known. Right, given x1, this is right. So you put these bounds, and the sum rate is upper bounded by the joint mutual information. That's the answer. OK, so let's recall what is the standard proof. OK, so the standard proof is so first you prove weak converse, right? You say, OK, by Fano inequality, right, the sum of two rates cannot exceed the total mutual information being pumped through the channel, right? Now this is a memberless channel, so it decomposes, right? So this can be written as sum of per letter, right? OK, now the second, so this is the first constraint, right? The sum of two rates is always upper bounded by the sum of mutual informations, right? Here the distribution of x1 is uniform on one code book, and x2 is uniform on another code book, right? OK, so then now you say, all right, if Gini gives x1n to the decoder, right? So then probability of error cannot increase, right? So OK, well then if x1 is known at the decoder, then the job of decoding x2 becomes communication through this conditional channel, right? And again, so by Fano inequality, R2 should be upper bounded by this, right? OK, so then you can conclude that R1, R2 belongs to right, this convex combination of these pentagons, right? OK, so that's the converse, right? Nothing fancy here. It's also super misleading, this proof, actually. Yeah, because it sounds like this is single user stuff, right? But it's completely different. I mean, you will see in a second. So there's so many open questions about this proof that it's mind-boggling. But superficially, it sounds like it's nothing different than single user stuff, right? OK. All right, so what's the standard achievability proof? Well, again, depending on how you're taught in your information theory classes, you use some sort of, right? So of course all the proofs use random coding, right? You generate code books from two distributions, right? x1 and x2, and then you decode via joint typicality, where, as I said, what I wanted to say is the definition of joint typicality depends. If you're Hungarian trained, right, then it's Chisar and Kerner. If you're sort of United States trained, it's Cover and Thomas, right, and anthropic typicality. But in any case, this is some sort of joint typicality, right? So then, right, so what happens is you say, all right, so there are this many possibilities for error for the joint typical erroneous code word where both of these indices are wrong, right? And each one happens with probability blah, right? And then with probability m1 minus 1, you guess one correctly, but the other incorrectly, right? Such pairs happen with probability of this. So then just do the union bound, right? That tells you that, OK, if m1 times m2 less than this, then you're good, right? There are no jointly typical pairs where both are wrong. This tells you that there are no jointly typical pairs where one of them is wrong, and that's it, right? So that's the end of the story. Okay, so what I wanted to go carefully over is what happens in the brain of the decoder here, right? And also how to do it in the finite block length stuff. Okay, so let's do it carefully. I wanted to take a break at the 1 hour mark. Yeah, I think that's about right. Okay, so let's generate right. So there will be 2 code books, C1 up to CM1 and D1 up to DM2. These are 2 code books, and I generate each code word, as I said, independently, sampled from product distribution of copies of PX1. Okay, so let's suppose the true message is W1 equals I sub 0 and W2 equals J0, 2 indices. Right? Usually we take them to be 1, but okay. Right. So now decoder sees YN. So what should it do? Right. Okay. So let's sort of slow down a little bit and just concentrate right at this moment. So your decoder, right? You see the output. Here's the question: how is this different from decoding a product size code book? Right. So you know that there are M1 times M2 possible pairs, right? Each one of them potentially produced this code word, right? So how do you, I mean, why are we talking about this, right? It seems like this is a standard decoding of a single user code, right? Okay, so the problem here is, of course, that, well, if this is I0, J0, right, then this code word is indeed, so the code word where both indices are different, right? The statistics of the output it generates is indeed like in a single user situation. However, if you take a code word which is here, right, which has one entry matching and the other, right, so one index is correct and the other is incorrect, right? This is like you're doing random coding where you select 2 halves of the code word independently, right? And then of course, right, so when half of it is correct, the other half, right, varying the other half changes the statistics dramatically, right? So that's why in some sense, when you do multiple access coding, there are 3 constraints you need to satisfy, right? This width should not be too large, because if there are too many contenders to fool you, right, if this table is very, very fat horizontally, right, then you cannot distinguish between too many fellows, right, in the horizontal row, right? So that's the idea here, right? Okay, so how do we do this? Okay, I skipped the finite block length part, the proof, but the summary is that, okay, so if you study finite block length achievability bounds, right, so then so you know that a good test, right, so you look at this table initially, right, you're given yn, you put it aside, and you draw this M1 cross M2 table, and you start to scratch your head and eliminate guys which do not seem plausible, right? So that's how decoding proceeds, right? So what's the good test to eliminate the guys, you know, outside of this cross? Okay, so that the test, again, from sort of standard stuff, is to do log likelihood ratio test, right? So you take, right? So this is the conditional distribution generated by a code word, right? By a suspected code. So you look at this entry and say, okay, so this is the distribution which should have been generating this code word, right? And you divide it by the distribution which is like the average distribution with respect to, right, generated by a typical code word, right? And then you test that. If it significantly deviates, right, then you remove it from consideration, right? And this is guaranteed. So the only guarantee here so far is that it's guaranteed to not remove the correct code word, right? But then if you apply union bound, you know that with overwhelming probability, after applying this procedure, what you get is a cross shape, right? So this is what happens in the decoder. The first test is just do the single user decoding, right? And then after you eliminate it, you will get this situation, right? Okay, so now once you get into the situation, of course, right? So if you were the decoder, you'll say, ha, excellent, right? What do I do now? Now I just have to decode one of the 2, right? So I have to eliminate this across this row and across this row. So how do you do it? Again, you apply a standard test, right? Now you condition, if you are eliminating across the vertical row, right, then you're just applying this information density threshold test. Okay, and so once you get once you proceed like this, right? So in the end, you get that you have to do 3 tests. If you select the thresholds carefully, then everything lines up. It's probably too fast, but you need to go over slides later if you're interested. And as I said, I'm very happy to answer over email. So if you have later questions, right? But the idea is that you do these 3 tests, right? And at the end of it, with probability 1 minus this, you will just have 1 entry left, right? So that's the philosophy here. Right, and as I said, because all of these quantities are central limit-like, right? These are sum of IIDs. You can see that any R1, R2 within 1 over square root n distance from that boundary is achievable, right? So again, so this leaving boundary as n progresses, right? It evolves in some strange way, right? But it approaches this fundamental boundary with speed 1 over square root n at least, right? So this is the achievability part. Right, so as I said, decoding T12 is like decoding a single user M1 cross M2 code, right? So you can think of it as LDPC plus, if you use LDPC code, then you have LDPC part and LDGM part, which is combination, right? Because your outputs are combinations, the sums of 2 entries, right? So this is like you can sort of, right? So another art which we learn in information theory, right, is how to transform this random coding abstract stuff into actual silicon, right? That's the stuff that is missing in some other disciplines, right? So we do these proofs, but in the back of our minds, we also know how to implement this, right, in practice. So this is a good thing. Right. Right, and so and actually, so I said that you need to eliminate the cross later, but you can check that unless you are very close to the upper boundary or the lower boundary, which is not the interesting regime actually. The interesting regime is to be somewhere on the flat on that side, right? On the sum rate optimal side. So unless you're close to that, then you don't even need the second 2 parts, because you will only get one entry remaining. So this is another cool thing to remember. Okay. Yeah, but and also, right. So another interesting thing to remember from this proof is, once you start applying this pentagon characterization to actual channels, sometimes it sounds really magical. How is it possible that 2 guys, right, they both send some stuff, right, they collide all the time, and somehow you manage to extract them sometimes with 0 error, right? This sometimes looks very counterintuitive, but the idea is always that, after applying some standard decoding for single user stuff, right, you essentially can guess one of the messages, right? And then you condition on it or subtract it, so you do successive interference cancellation. So this is what I'm trying to say. That this random coding proof, you can stare on it for a week and discover new things about it, right? So that's it's a really, it hides a lot of interesting stuff that is happening when you just read these 5 lines of joint typicality, blah, blah, done, right? So this is, okay, so hopefully I convinced you that there is some fun stuff. Okay, let's apply this. So here's just like there are 2 kings of the single user channels, BSC and AWGN, right? There are 2 kings of multiple access. One is the noiseless binary adder channel. Okay, so what's the channel? You take each user is allowed to send 0 or 1, and the receiver sees their real sum. So the receiver sees 0, 1, or 2, right? Okay, no noise, completely noiseless channel, right? Okay, so you can apply this theorem, right? You can ask the question, what's the maximal sum rate you can achieve? Okay, so it turns out the unions of those pentagons, by the way, we always give you, right, in the sort of those basic examples, by we I mean teachers of information theory, right? We give you examples where the union of the pentagons is actually achieved by some one fattest pentagon, right? And then, so we get used to this idea that the capacity region is always a pentagon. Actually, no. You can do multiplier channel, for example, y is equal to x1 times x2, then it becomes curvilinear. So of course, union of pentagons doesn't have to be a pentagon. But okay, in this example, it is. So you just need to consider pentagon generated by 2 uniform half distributions. Okay, so the capacity region here, the sum rate, the maximal the maximal sum is given by just this seemingly simple maximization, right? H of A plus B. So you get simple calculation that the entropy of the sum of two Bernoullis is 3/2 log 2, and you cannot exceed it by skewing two Bernoullis. Okay. One thing to notice here is that this is actually a very non-convex optimization, which should be suspicious, right? Because that's what I was saying when I said that it's misleading to think that single user, that multiple access is like single user coding, right? In single user, when you maximize over distribution, it's a convex problem, right? Here is not convex because of the product structure, right? A and B should be independent, right? So that's why it's a miracle, really, that we were able to solve multiply. So there's no miracle that we can't solve any other network problem. That's obvious because they are not convex. But here, it's really a miracle that we were able to solve it. So, okay. Anyway, so I'm departing. So here's the right. So I like to challenge my smart computer science colleagues, right? I say, okay, so I mean, so how do you? I mean, how's it possible, right? Each guy sends one bit, and together they can send 3/2, right? Actually, even worse, let's think about this point, right? You say one guy, look, you are going to send at full rate, right? You will send zeros and ones, right? You have zeros and ones, you full rate 1, right? So all your entries are meaningful. You cannot lose any entry, right? And yet, on top of this, isn't it, I mean, it's super magical, right? On top of this, right, one user sends at full rate. On top of this, the other one can still send half a bit. I mean, this is really mind-boggling, I think. I don't know, if maybe only to me, but the more I think about it, the more I like it. Anyway, so, but actually the explanation is, of course, very easy, right? If one user sends at the rate 1, right, then from the point of view of the other guy, what does he see, right? If he sends 0, the output is either 0 or 1 with probability half, right? And if he sends 1, then the output is 1 or half, or 2 with probability half, right? So how do you call this channel? Come on, guys. I mean, right? You know, it's binary erasure channel, right? With probability half, right? Okay, so capacity of it is 1/2, so that's why you can send on top of it, right? So essentially, every time the user 2's code sees a 1, he treats it as erasure, right? Okay, this also brings about a funny solution to this problem, right? So what you do is you say u. So who is u? I think I flipped here, right? Yeah. So ua. You are going to send UB, you're going to send at full rate, right? You're sending zeros and ones, right? UA, you will send using a good binary erasure channel code, right? Okay, he says, all right. So then the first thing the decoder does is he just decodes this message AN, right? Using standard, say, LDPC or something, right? Belief propagation decoder, peeling decoder, right? Subtracts this decoded message and then gets a clean other channel, clean other code word, right? So not only it's possible to do it, it's also, right? You can also do it with completely single user codes, right? What I would call low complexity solution, right? Okay, so it's very nice. Okay, is there anything interesting we can ask about binary ether channel? A lot, and it's very, very depressing actually that there's lots of open stuff on this back, and I spend many times, and every time I get a smart undergraduate, because for graduate it's a little bit dangerous, I'm sorry to say, to go here, right? Because if you don't succeed, right, you don't have anything to put in your thesis. So I only give it to undergraduates, this question, right? Because they can fail, they have a chance, right? Okay, so right, so what's the question? Okay, so first of all, if you do finite block length achievability, right? So then what you can prove is that you can achieve some rate which is 3/2 minus this penalty, square root 1/4 n q inverse. Okay. So here's the problem. Can we prove that the sum rate is upper bounded by 3/2 plus square root 1 over n? Very simple. Actually, if you know a little bit about finite block length, right, you could say, Yury, shouldn't you ask this to be negative? Because historically, that's how the first proofs of those classical era came about, is when people started asking, do you approach capacity from above or from below? Right, that was the question. So we have no idea here, really. So there's no, I mean, forget about asking this. This is very tough, right, to even, I'm asking just, can you just prove with the positive k epsilon? Are we even approaching sum rate capacity with speed square 1 over square root n? Nobody knows. So the best known estimate is this one with square root 1 over n log n due to Alsavede.
So I have a question. Do we know that the gap from the capacity region is uniform for finite lengths? In other words, is this sum rate is the best point to achieve the sum rate on the equal rate line, or is it possible that you may actually be able to achieve something better outside of the equal rate line?
Okay, so Krishna's question is whether random coding achievability bounds for other points give better numbers. I think the answer is no. But yeah, so my personal story with this is the following. So after I'd done my thesis, it was all about single user. I said, okay, time to move to multiple user, right? Let me solve multiple access channel, right? Because the capacity is known, right? So, right? Nobody can improve this bound. I mean, even to minus, minus something. So this is the best. This is the best bound we know. And it's just Fano inequality. So this is the famous. So this is the open problem. I do not recommend you to do unless you already have a faculty job lined up or you're an undergraduate. So actually, I don't want to discourage you. Okay, you might, yeah. If you're watching this online and you think you can do it, please by all means do it. But just be warned. I mean, this is a tough question. Okay, so now there is one path to solve this, which we outlined with a smart undergraduate then, now a graduate student, but he still wants to do this, Ganesh Ajanagaddi, so he's at MIT. So we noticed that actually this would be implied by the following much simpler conjecture, seemingly simpler, right? So you're asking about maximizing Rényi entropy, right, for the sums of two independent, so an and bn, right? Both are distributed on the hypercube, right, 0, 1 to the n. They are independent, and I'm asking you to maximize the Rényi entropy of their independent sum, right? So the conjecture is that this is achieved at the product distribution, right? So this is the best distribution you can pick is uniform on the hypercube, uniform on the hypercube, and then you get this number, right? Okay, so now for alpha equals 1, when you get the Shannon entropy, right, this is easy, right? Because you say, okay, h of vectors is upper bounded by sum of individual marginal h's, right? And those are solved in single letter, easy, right? So the question, okay, so when I noticed this, I said, okay, done, right? But yeah, so actually, even checking this for n equals 2 is not a piece of cake. So yeah, so I was planning to show you how it implies this, but now we're due for a break. So anyway, so if you have time, so there's some very nice, essentially one-line proof where you just apply data processing. So okay, so here's the summary how you show that this implies this. You just need to apply. First of all, you need to understand in your head that weak converse, when we apply Fano inequality, is exactly just one idea. You're applying data processing to KL divergence. So this is I mean, I don't know, it was an important milestone for my personal development when I realized this, that Fano inequality is nothing else than just applying data processing to KL divergence. And why is this important? Because there are many other divergences, right? You can choose your divergence and you get other impossibility results, right? So if you apply it to Rényi divergence, right, with alpha, which is 1 minus 1 over square root n, and if this is true, then this implies that. So you can just check this, okay? And if you want, I mean, I put it on the slides how to do it. All right, quick summary. We learned that, yeah, so sorry. So this is the K user, right? So the quick summary before we go on the break, and hopefully some of you return. So, right, so you can generalize all of this to K user Mac, right? Now you will have this kind of constraints. Sum of rates over subsets are upper bounded by this kind of mutual informations, right? And now you need to take union of these pentagons. Again, it sounds like it's becoming more complicated, but frequently you can do it, like for Gaussian Mac. We'll do it shortly. Now there is one thing to remember is the following. Why you never seen in the literature finite block length bounds for Mac evaluated for anything more than 2 users? Because if you put 100 users here, right, remember when we were doing this decoding, right? We had to eliminate first, right, all the guys outside the cross, right? Well, now the number of subsets you need to check is, I mean, the number of such tests, is exactly the number of subsets of the universe of size 100, right, which is 2 to the 100, right? So now just evaluating these numbers becomes absolutely impossible. So I can write down the achievability bound, right? Okay, so there's going to be this probability of a union of 2 to the 100 events. I'm pretty sure it's going to give you the right answer. I just cannot compute it, right? So that's a funny challenge there. If you get to it, I'll try to describe to you how this can be overcome a little bit. Okay, so what is new in the today? So this is the old story. Okay, so the new interesting thing is the following. First of all, you need to think about different scales. So it's wrong, and it's wrong in the nowadays world to do the standard old assumption that you fix k to be 5 and take block length to infinity. Why? Because I have k equals 5 cell phones transmitting simultaneously, and all of them are super greedy. They want to transmit huge data, right? Huge amount of data. This is not true anymore, at least not in the IoT kind of setting, right? So you need to scale number of users and block length simultaneously. And then, of course, all the hell breaks loose, right? So then, you cannot apply any of this typicality stuff, so everything becomes super, super different. Okay, and the second thing is, I will argue about this later, but you can no longer define probability of error in this simplistic way. Because when you have hundreds and thousands of users, misdecoding one, you don't want to treat it as complete failure of decoder, right? Decoder still output 999 others, right? You don't want to say you failed, right? So the more correct definition of this. Okay, and also a funny last twist is that you can think of random access as just requirement that all users use exactly the same code book. Remember, it was important for me, for all these proofs, right, that users generate their code books separately, independently, right? If you put this constraint that all code books are born equal, right, because they all use the same modem, or when the cell phone wakes up, right, it doesn't know its identity, right, because he knows his identity, but his identity is unknown to the base station, so he communicates as if it doesn't know. Okay, so this is the third twist. Okay, so this is the summary, and then let's go on a 10-minute break and hopefully come back. Yeah. Okay. So see you in 10 minutes at 10. So all right. So right. So let's talk about Gaussian k-user MAC. Right. So so first of all, why people care about k-user Gaussian MAC? Well, of course, that's because our cell phones connect to base station, right? So we have k transmitters. Their waveforms combine over the air, right? And then the receiver sees this real combination with some white noise added by the amplifiers, right, at the receiver. Okay, so right, so again, just to recap the multiple access story and the coding story, right, is that you have all of these different signals, right? They pile up on top of each other, and you see the completely garbled output, right? By you, I mean the base station, right? And the job of the base station is to look at it carefully and be able to separate perfectly, right? To undo this destructive operation, which is addition, right? You add several numbers, and you get one number. Okay, so right. So when I phrase it like this, actually, right? So it might sound very strange. How is it possible, right? So I want you to think for 1 second, not as an information theorist, but as an engineer, right? How can this be possible that you just lump a lot of things together, right? You look at their sum, and then you're somehow able to undo this operation. Okay, so of course engineers looked at this way before any of the IoT happened, right? So they invented the following several ideas, right? They would say, all right, well, how can you disentangle several things? Well, they have to be orthogonal in some sense, right? Otherwise, an engineer right? So as an engineer, you just think it's impossible otherwise, right? If two things somehow collide, you cannot separate them. So there are several ways how you can orthogonalize these resources, right? You can split by frequency. That's what radio stations do, right? So they all send to our, well, okay, I guess radio stations. Yeah, it's a bad example because nobody listens to radio. I listen to radio every morning, but I think I'm a minority here. Anyway, so then they split by frequency, and that's how their signals do not interfere, right? So another idea is to split by time, right? This is how we organize lectures, right? So lecturer speaks, and then you ask question, and I speak again, right? So this is TDMA, all right? And then, okay, so then you can, of course, pick a different basis, right? I mean, you don't have to, so this is one basis, right? This is orthogonal basis in Fourier space. This is orthogonal basis in time domain, right? You can you can pick orthogonal basis in some other way, and that's called CDMA. Now, OFDMA is just a buzzword again. It's essentially just picking a different basis. Okay, so, right. So now the problem with this is that these are all orthogonal schemes. And why this is not a good idea for IoT is because it requires you to partition resources between the users which you know will be active, right? So when you do it remember my first slide, how cell phone works, right? So cell tower can afford it because it decides who will speak, right? So it can completely orthogonalize resources. But if you're in the mindset that the sensors wake up by themselves and blast their packets, right? I mean, for them to not interfere, you have to somehow smartly partition them in such a way that regardless of who wakes up, they never collide, right? But this just means that dividing the precious spectrum bandwidth time product, right, between all possible sensors, of which there are millions, right, and then there are very few active, so it's completely underutilized system. Okay, so that's not a good idea, it seems, right? Okay, so that's why I want you to, right? I want your brain to start thinking, how would I do this otherwise, right? So let's think about it, right? So first of all, this sort of pi slicing philosophy comes from the Kotelnikov, Nyquist, Shannon, Slepian, Pollock, whoever theorem, right? Sampling theorem, right? So that if you just take W bandwidth and duration t, then you have 2WT real degrees of freedom, right? And now you can just partition them as you please, right? Okay, you select a. Okay, so, but we are in a regime where k is greater than n, and the first question I want to ask you is it even possible to have number of users? Can you, I mean, right, so if you challenge the standard communication engineer, you say, I have, right, my 2WT is 100, can I send 200 messages across this? He would say, no, right? How, I mean, you cannot divide, right, a degree of freedom into half a degree of freedom, right? It's atomic stuff. Okay. Well, actually, the answer is very simple, right? Of course you can, right? Because one example is you have 1 degree of freedom, right? And user j just sends 0 if he wants to send 0, or 2 to the j if he wants to, right? And then the real sum, you just do the binary expansion, and then you just read off the numbers, right? Okay, so it's a very silly, right? So in some sense, this pi slicing is completely bogus, right? Or maybe it's not, right? Because you see, so there is some cheating here going on, right? That it's very unfair for the last user, because he is sending signals of size whose power is 2 to the 2k, larger than the first guy, right? So it's not very fair. So let's restrict them a little bit, right? Okay, so let's think about the following challenge, right? You have users which are only allowed to send plus minus 1. So you cannot do this cheating, right? Where essentially there is interference free, right? Okay, so can you have k much greater than n, right? That's a basic question. Okay. Right, so let's think about what we are asking, right? So we are essentially asking about capacity of the k-user binary adder channel, right? Why? Because each entry can be plus minus 1, and we are observing, let's say, noiseless even sum, right? Okay, so it's a moderately simple exercise to show that the maximum entropy of this sum is actually achieved when you select all of this plus minus 1. It's funny how information theorists, there are several papers, just assume it for granted. And then Larry Shepp actually published a paper where he actually rigorously proved this. So technically this is, yeah, so anyway, so, right, so you can compute that the maximal entropy achieved at the output is actually entropy of the binomial distribution. And, right, so this is about 1/2 log k, right? Okay, so this means that if every user wants to send 1 bit, right, then his frame length for k users, right, we should be possible to do it with 2k divided by log 2k frames, right? So again, the game is I have large number of users, right? Each one wants to send 1 bit. His entries are only plus minus ones, but he can select them in a smart way, right? He needs to select 2 waveforms, which are both plus minus ones, right? And after we see this, right, so the length of these vectors is going to be n. What's funny is that it's significantly smaller than k, according to information theory predictions, right? But it's interesting. Can we actually do it? Just to visualize some sort of, I mean, I wanted to include some kind of explicit construction somewhere. Okay, so here's a funny construction of 2 Armenian folks, Khachatryan and Martirosyan. Yeah, you can actually do it, and even with 0 error. So here's how. Okay, so first of all, right, so if you wake up in the morning and you want to select a plus minus 1 basis in the real space, this should be your first choice, right? The Hadamard-Walsh matrix, right? So you just select this block, and then you repeat it. You take tensor powers, right, or you do this construction, right? Okay, so the rows and the columns of this matrix are orthogonal, so it's a nice orthogonal basis, right? Okay, so now if I'm a user, right, so if I take this matrix, right, then user 1 can modulate this row, right? User 2 can modulate this row, user 3 modulate, right? And then this is orthogonal modulation, so you can perfectly, even if they're sending reals, right, you can disentangle them. But what if they only send plus minus ones, right? What if they only change polarity? Maybe you can add a little bit more vectors here, right? And that's what these 2 folks noticed, right? So they said, look, right? Because you're not exploiting full set of possibilities when they are sending plus minus 1. So here's what they said. They said, all right, so let's take the first basis, right, is going to be the same. But for the second basis, let's add 1 more row, right? Okay, so and then you can check. I mean, I wrote a slide on this, but you can check yourself, right? So that actually all plus minus 1 combinations of rows here are distinct, right? So now you have 5 users sending plus minus 1s in 4 degrees of freedom. That's funny, right? But what's even more funny is that you can actually induct here, right? So you proceed like this. You define this matrix, right, where you take the previous one, you do this Hadamard-Walsh, right, block here, and then you add the matrix of all ones of size 2 to the m by 2 to the m, the same matrix with inverted diagonal, right? So you do this construction, okay, and then you cross out the top row. That's the funny operation. So this is how you define the next, and you just do it by induction. Okay, so I wanted to spend time on showing why this works. I think I'm going to skip this, but this is the entirety of the proof. There is really, I mean, what you need to notice is basically that the contribution of the bottom row. So if right, so this matrix AM or A tilde M, right, it has 3 blocks, 3 natural vertical blocks, right, X, Y, Z. Right, so then you can partition the users into 3 groups, right, X, Y, and Z. So all of these are row vectors of plus minus 1s, or 0 1s. Actually, it's equivalent. We can just prove that if it works on 0 1s, it works on plus minus 1s by translation. So, right, so then the output consists of 2 row vectors G and H. If you take their difference, then after a little bit of algebra and taking mod 4 of entries, you figure out that you can actually decode the bottom guys. Once you decode the bottom guys, you subtract them, and you're back to the question of decoding for AM. So that's the funny idea. Okay, so now let's ignore this proof. Let's go back and then compute the dimension. So you can actually compute the dimension, right? So the number of users supported so the size of the matrix is 2 to the m, and the number of users it supports is m over 2 times 2 to the m plus 1. Okay, so what this means is that the number of users per block length, right, is exactly the optimal scaling which you obtain from capacity. So this is a really funny construction, which I think awaits its hour in the age of IoT, right? So we somehow need to. I don't know why. I don't know how. Sorry, but that's why I wanted to plant in your head that there is some smart ways to do modulation and support many more users than just the standard pi slicing kind of idea suggests. Okay, so let's right. So this was and of course this also shows that you can explicitly achieve the sum rate capacity of a k-user binary adder channel, right, up to some corrections, with even very short payloads, right? Each user is sending 1 bit, so you don't go to any infinite block length, right? So it's as fine a block length as you can hope. You just send bit by bit and decode bit by bit, so complexity is not an issue. Again, right? Okay. Right. So some reflections, right? When user inputs are constrained, for example, to ±1, you can definitely have number of users exceed the number of degrees of freedom. Another interesting thing is that total information transfer grows with k, right? So the entropy. So this is how we should think about this, right? So remember, networking people, they think of collision, right, as multiple access operation is collision, so it sort of kills information, right? But for us, we actually say no, it's a good thing, right? Because the total output entropy, right, sort of can scale as logarithm of the number of summonds, so it's a good thing, right? And the more users, the more information you transfer altogether. And this is reminiscent of the scaling in Gaussian MAC, where number of users also increases capacity logarithmically. Okay, another interesting observation is that there's lots of smart ideas in MAC calls. This was just one random super simple example, and there's a huge literature. As you can imagine, I mean, how many smart ideas are there in single user codes, right? Now you have many users, so it's a lot more flexibility. Now the beauty here, and this is some philosophical part I wanted to reflect on, right? So this is why I personally love information theory, right? So all of these smarts for us are completely subsumed in this funny formula, right? In this closed form, right? So somehow information theory provides the structured thinking here, right? I mean, if I showed you this code construction, I say, can you say something general about this kind of construction? You'd say, whoa, I mean, this is so special, right? There's so many tricks, induction, plus minus ones. But somehow for information theory, right, it's very structured. Yeah, and of course, what I'm suggesting here is that, so it's a little bit like all the, right, so I mean, if you look at this formula, it hides a century of work on how to actually achieve it, right? Anyway, so it both gives power to this kind of formulas, and of course, sort of power to people who try to achieve it. So it's a funny situation. All right, so let's talk about Gaussian MAC. So this is the Gaussian MAC, right? So we have x1, x2 now with cost constraint, right? The expected square is required to be p1, p2 for 2 users. Noise for me is always IID 0, 1, so there is never sigma square in my talk. All right, so simple exercise, which I'm not going to repeat. I'm sure if you took any information theory class, you must have done this, right? That Gaussian achieve maximum mutual information, right? So then here you just do this, right? The sum, the power of this term is p1 plus p2, so the mutual information of the sum is upper bounded by this. And of course, separate mutual informations. Once you condition on the other xi, on the other message, this just becomes a vanilla Gaussian channel. Okay, so this is the capacity region, right? Okay, nothing more to say. But actually, I mean, this is a simple capacity region, but then you can ask questions, okay, what are some low complexity solutions, right? Because to achieve this, what do you need to do? You say, all right, I need to jointly decode 2 users, right? Meaning, instead of going over all 2 to the k messages, right, I need to go over 2 to the 2k messages, or little k, right? The number of bits you send. So it's like, okay, so that's why people, so those modulation ideas have a place here, right? So for example, you could do TDMA. You could say, all right, I'll partition my block into some piece where only user 1 sends, and some other piece when only the other user sends, right? So then you achieve these rates, right? Okay, so this is the line you achieve, very good, okay? Of course, it's far from the optimality, but it's very easy to implement, right? Just partition resources. Okay, now, right, and the good thing is that you also have a very low, okay, not very, but low complexity decoder, which just decodes each user separately, right? On the first partition, you decode first message. On the second part of block length, you decode the second. Okay, so what about FDMA? So how do you think of FDMA? Well, when you do FDMA, you rotate the bases, right? And so now, if you partition the block into lambda n, you can put more degrees of freedom, more power into each coordinate, right? So instead of power p1, like before, you can put p1 over lambda, right? Because once you translate back into real time, you sort of will get on average the same power, right? The same per coordinate power n p1. Okay, so this achieves this some nice curve, right? So you can trace this R1, R2, and then, okay, so the important thing is that it touches the sum rate at one point, right? So yes. So if you put lambda star equal p1 over p1 plus p2, then you exactly get the optimal point. Okay, so this is a very cool thing because you see, for example, when powers are equal, you touch it at exactly the most interesting point, right? Which is the point of largest symmetric rate, right? So yeah, so the point where, so interesting regime for us when you think in IoT kind of, right? So where all sensors are born equal, they all will send with the same rate. So the interesting point is always what's the largest symmetric rate? Or what's the largest point intersecting this straight line? And that's exactly where FDMA is optimal, right? So you could say, all right, so there's nothing, so we don't, why do we have to study anything else, right? The FDMA is so good. Okay, yeah, so we can, as I said, I mean, one reason is because power is imbalanced, then, and so, but let's just keep going. So what's the other simple solution? That's what's called treat interference as noise. So it will be an important player for us. Right, so what you do is you say, okay, so when I'm decoding x1, why don't I think of x2 as just Gaussian with variance p2, right? If I do that, then from the point of view of decoding x1, I'm just doing communication across Gaussian channel with slightly higher variance of noise, right? Instead of 1, it's 1 plus p2, right? Okay, so then you can achieve this rate, right? You will have R1 equals 1/2 log 1 plus P1 over 1 plus P2, right? And R2 is going to be, right? So, okay, the beauty here is that both users are, decoder is again single user, right? Because every decoder, it doesn't try to get, right? So, I mean, when I say single user, right, what would be the smart decoder do, right? He first tries to decode x1 and then says, okay, if this is x1, what's x2, right? And then go back and forth, right? Sort of, right? Try to, because once you know x1, you can subtract it and try to do x2, right? And this decoder doesn't do anything like this. Just says, okay, let me just brute force it, try to decode x1. Okay, so what's the point? This is the point here, right? So this is exactly when you, from these corners, you drop these two lines and intersection. This is what you get, right? Okay, so it seems like it's far, but you will see why I'm talking about it. All right, so now let's consider corner points. What about corner points? Okay, so now corner points coordinates are this. It's 1/2 log 1 plus P1 divided 1 plus P2, and okay. So when you look at this, you can say, wait a second, this is what I can achieve with treat interference as noise. By the way, when I was a sort of a junior guy, it annoyed me extremely that people just say this, right? But when I say you can, right? So what, I mean, when I say you can treat this as Gaussian noise and I put this as capacity, right? It's a little bit wrong, right? And you should be, I mean, if you're mathematically trained, right, you should be very like on your toes, right? Because x2 is a code word, right? So it's not Gaussian. So why am I just suggesting that, just replacing it by Gaussian noise? Sometimes people will do even worse. They'll say, but Gaussian noise is the worst. Oh, this is super wrong, right? This has nothing to do with this capacity. So what's really happening is when I say you can achieve it, here's what I'm actually, okay, let me go back here. This is important. What I'm actually doing, I forgot to say this line, to stress this line, right? What I'm really doing is I'm doing random coding with this decoder, right? I'm not saying that if you use for x2 your favorite polar code, then R1 can decode at this rate. No, this is wrong. This I don't know if it's true or not. But what I'm saying is I'm doing random coding, right? And while I'm doing random coding, then x2 indeed is purely Gaussian, right? And so then there is a way. Okay, so, right? So it's very important here that when I say that you can achieve this by single user, I don't mean you can achieve it with vanilla off-the-shelf polar code. This I do not know, and this may be wrong actually. Right? So this is what I want to stress. This just means there exist codes which are decodable by single-user decoders. Right? Okay. So let's go. So let's look at this equation here. Right? So okay. So this looks like we can achieve this by just doing single-user decoding, treating the other user as noise. Right? Okay. But then you'd say, wait, why can't I subtract that after I decoded it? Once I subtract x1, right, x2, this job becomes just vanilla Gaussian channel, right? So, and this is exactly what the rate pair you achieve, right, fortunately. Okay, of course, this is, this is what's called tin plus 6, successive interference cancellation. Right? You first decode one with tin, and the other one you decode after canceling the first guy, right? Okay, so the important thing to notice here is that, again, here we do the union bound on the probability of errors, right? If this was an error or this is an error, right? So as the number of users scales, especially scales linearly with the block length, this is completely wrong, right? So anyway, so there's lots of issues which arise in the 5G sort of world. But okay, but for now, let's be happy, right? For 2 users, it's all fine. 2 users, humongous block length, everything is great. You decode one, subtract it, and use 2 single-user decoders. There exist codes for which this architecture works, and you achieve corner points. Okay, so looks like we are in good shape, right? So I showed you how to achieve 3 out of this line, right? 1 FDMA somewhere in the middle, 2 corner points. So for some time, people thought that the rest of the points wouldn't be possible to achieve by this kind of, single-user type decoders. But then, okay, so Rudy Urbanki, when he was still young, he invented this super cool idea, which is called rate splitting, right? So you say, hey, why don't I split this one big user into 2 single users, or into 2 virtual users, right? Let's call them 1A and 1B, right? So you just split your identity, but now you need to partition the power too, right? And partition the rate. But otherwise, right, you do the same thing. Okay, and now you just decode basically half of user 1 first using treat interference as noise, then you subtract it, you decode the second full user, right? And then you subtract him, and then you decode x1b, right? So if you check here, what happens is, first of all, the sum rate is optimal. So you are landing somewhere in this line by doing this, right? So I'm still doing treat interference as noise and successive interference cancellation, right? Just in different order. I'm not canceling the full user, I'm only canceling part of the user, right? Okay. And so then in this way you can achieve any point. Okay, so that's the end of the story, right? So not only we can draw the capacity region essentially with off-the-shelf, there exist single-user architectures, right? And now there is a leap of faith that we believe that if you now plug into this architecture off-the-shelf polar codes, LDPCs, turbo codes, whatever your favorite thing, they will probably perform as advertised, right? So that's our belief. And then you have to verify it by simulations. Okay, but the good news is that, okay, everything is fine. All right, so is there anything else to do? Well, let's look at the k-user GMAC. Interesting. Yeah, all right. So I'm also, okay, because now there's too many parameters, so let's fix the powers. And also, again, in the IoT kind of mindset, right, all the sensors are born equal, so they're interested in the same rate and they have the same power, so P is, okay. So then you can check that the sum rate is given by this half log 1 plus kp, right? Okay, so Right, so what do single users, and then the story is the same, right? So single user decoder, FDMA is optimum at a symmetric rate point. So tin plus SIC achieves all vertices, all the corner points in this, now it's a polytope, right? Strange. So now you can use this Rudy's rate splitting idea, right? To achieve any optimal point, the optimal sum, right? Okay, so is that it? Okay, so let's see why people are still thinking about, or at least were thinking about K user GMAC. Okay, so you see, so the sum rate capacity, let's reflect on the first thing, right? So the sum capacity, right? If you have K users, all with same power, right? The networking folks would say, well, they can still send half log P, log 1 plus P, right? But actually, we know that because of physics, right, you can actually, they all together can send a lot more, right? Because their joint power is bigger. Okay, very good. So I always thought this is a fantastic thing, right? So that, okay, as K grows to infinity, the sort of, right, the sum rate increases. So, okay, so let's look at this a little bit more carefully, right? So what about the per user the per user rate? It's also the largest symmetric rate in this case, right? If you divide this by K, then you see logarithmic growth is nothing compared to 1 over K decrease, right? So actually symmetric rate goes down to 0 very, very quickly, right? Okay, so even though many users is a good thing from the point of view of the system performance, the per user performance actually suffers, right? Okay, so now to go further, right, we need to introduce this key performance metric, energy per bit. Okay, so how is it defined? It's the total energy spent divided by twice the total number of bits. Don't ask me about twice, it's just a convention. Okay, so so if you plug this in, this formula, right, the total energy spent was Kp, or n times Kp, right, the block length, but n cancels, right, divided by log 1 plus Kp. Wow, it explodes to infinity, right? So this is the interesting situation, right? So now you have K users. They all transmit more at fixed, if they work at fixed power. But per user, each poor user transmits fewer bits. And therefore, right, the energy per bit explodes. So this is a completely useless situation, right, from the point of view of system, right? Because, why would you want to send at the infinite energy per bit, right? You have a fixed ratio, okay, so for this reason, of course, whenever you think about K user systems with large K, you always want to operate at the regime where the total power is constrained. So as you increase the power, as you increase the number of users, all of them have to whisper, right? So, okay, there's two reasons for that. First of all, you don't want to burn the base station, right? Because Kp is going to be very large. And the second is, of course, then energy per bit stays bounded at least, right? Okay, so that's an important observation which you should remember. Okay, so what about spectral efficiency? So another important metric for communication engineer is the spectral efficiency, right? You pay a lot for spectrum, then you want to ask how many bits per bit per second per hertz am I sending in my system, right? Let's call it raw. Okay, so for the optimal system, right, we have this situation, right? The total rate is 1/2 log 1 plus Kp. Again, maybe it scales down with K, right? But this is true for every K, right? Okay, and actually you can re-express, right? You notice that, oh wow, both of them only depend on this total power Kp, right? So you can re-express energy per bit as this function. So what's shocking, and really, I don't know how many times I thought about this, right? It's really funny that it doesn't depend on K. So whatever number of users is, the optimal trade-off between energy per bit and the spectral efficiency is the same, right? And by the way, this number is also lower bounded by minus 1.59 dB, which is a famous, fundamental lowest energy. Okay, so here's how this plot looks like, right? This is spectral efficiency, bits per second per hertz, right? And then this is the energy per bit, right? So think of this as inverse of how often you change battery, right? And this is how much you pay, right? I mean, because why AT&T should care about spectral efficiency? Well, because they buy a certain spectrum, right? And then you do, I mean, then, and each customer wants some number of bits per second per hertz, right? So that's how they think about it. Okay, so this is the fundamental trade-off, right? Let's see what other systems. So what about treat interference as noise? Okay, so treat interference as noise. So you can write down the formula, right? K over 2 log 1 plus P divided by this total interference. Okay, so again, we are thinking K large, right? So I mean, this convergence is very fast here, so there is not really a problem, right? So then you get this funny formula, 1 over 2 base E logarithm of 2 times P tot over 1 plus P tot. Remember, P tot is the sum power, right? Okay, so you get this expression. And energy per bit, is, as usual, right, is just you divide total power by the spectral, by twice the spectral efficiency, right? Okay, so you get this trade-off. So what does it look like? How does it look like? This is how it looks like. Right. Okay, so what I'm trying to stress here is that treat interference as noise we saw is inside the capacity region. But one good thing about it is that it achieves the, right, so if you're operating at absolutely the lowest, you want to have the lowest energy per bit, you sort of suffer a little bit of spectral efficiency loss, right? But overall, it's, you know, maybe not bad, right? Okay, yeah, and the important thing is that you can never achieve more than 0.72 bits per real degree of freedom with treat interference as noise. So why am I keep saying about treat interference as noise? Well, because you see, okay, so you will see if it's so bad, right? Oh, by the way, so the orthogonal solutions, right, would be here, right here, right? So they're all optimal. Okay, so you see, so right, so let's think about, I mean, I'm trying to sort of undo a little bit of time because it was always a miracle to me why there was so much effort spent on CDMA, right? So I'm trying to explain, maybe I'm wrong, but I'm trying to understand myself, right? So, okay, so let's look at those two curves and say, okay, treat interference as noise is not that bad, right? It's very easy architecture. Everybody decodes treating others as noise. So let's try to achieve this, right? Okay, so now one thing to notice is that, remember, per user rate is rho over K, all right? Rho is the total spectral efficiency from all users, right? Okay, now, okay, so here's a small aside. For us, information theorists, right, you give me a channel of capacity half, or capacity, you know, 10 to the minus 3, I don't care. It's channel, it's a number, right? You can achieve it. Who cares, right? But for coding folks, right, and for communication, the first channel is a gift, right? It's very easy. You just apply rate 1/2 polar code and then or LDPC, and it's fine, right? It's going to work. But the second channel is a nightmare, right? I mean, so they would never try to directly do coding for this channel, right? You don't find good LDPC codes at this rate, for example, right? So what you do is you first improve the SNR a little bit by using some modulation. So use some front end, right? So to improve the SNR a little bit, and then you do coding on top. Okay. Now here's another issue, right? So if you want to do treat interference as noise practically, right? So let's go back to the times of Viterbi, right? And you actually want to implement system with K users, right? You have these codes which output plus minus ones. You have this theorem which says, hey, if you plug in, right, just a vanilla single user codes and add and treat the other as noise, it should just work, right? But then you say, wait a second, but my plus minus ones, they don't look Gaussian. Won't they fool the decoder? And of course they do fool the decoder, right? So how do you make that interference a little bit more continuous? Well, that's the brilliant idea of doing signatures, right? So what you do is you say, all right, now let's partition this huge block length into these little chunks of length capital N, right? And these are new super symbols, right? So when user 1 wants to send his bit B1 or his symbol B1, right? Instead of putting it in one square, he will modulate some length capital N vector, right? So essentially, right? So now, if these vectors are not very, if they are orthogonal, then you didn't lose anything, right? You lost a little bit in finite block length, but you didn't lose capacity, right? But if they are approximately orthogonal, then the funny thing is that, okay, did I put this here? Right. So it's taking suspiciously longer and longer from the click to, so I think it's gonna it's gonna die soon. So, okay.
Using good codes.
Yeah. Okay. So, right. So, yeah. So, okay. So, right. So okay. So this is the architecture which I'm trying to sell. Right. That instead of doing coding on the level of real degree of freedom, you do coding on the level of what modulates a vector. Right. So it's like I now have a two-stage scheme. Right. Okay. So. Right, so here's the idea, right? So, I mean, once you receive this in each super symbol of length capital N, right, you just do the matched filter, right? So you project ith user onto ith user signature, right, his vector. So he's modulating in one direction, right? So you get his message plus some extra noise, right? And now you see the thing. So now this is why this is beautiful, right? Because this extra noise, right, is going to be composed of lots of inner products. Right? Now, even if those guys were sending plus minus ones, right, these inner products will make sure that this is now becoming continuous. So in some sense, this makes it very Gaussian. Right? So this is why it's such a cool engineering solution to the problem. Right? When instead of just trying to think about how plus minus ones are not Gaussian, you just say, okay, let's do inner products, and now, okay, this is a very cool idea, right? Okay, so also, okay, now there is a question, how do you select signatures? And from the IoT point of view, and back in the Viterbi days, right, this is a good idea to just select them randomly, okay, instead of allocate. So if you wanted to do central allocation, of course you can just do orthogonal, right? Then they don't interfere with each other, it's perfect, right? But yeah, so it's very attractive architecture when you just let them, generate signatures essentially randomly, and then maybe on some low rate channel announce that, okay, I'm user blah, I'm using signature blah, and here is my 10 trillion bits, right, that I'm sending on some other channel, right? So it's just attractive architecture because there's no central synchronization. Okay, so you can check that, okay, so single user decoder sees effective SNR blah. So if we introduce this parameter beta, which is the ratio of number of users to this, what's called spreading length, right? Okay, so then you get this formula, for the effective SNR. Yeah, and the thing is that, okay, this convergence is very fast here, right? That's another. So if signatures are of length, I don't know, 20, then already two random spherical vectors are very close to have this inner product. Yes? Yeah, okay, good question. So the question is, how do we generate signatures with what distribution? Okay, the answer is it doesn't matter really, right? So what matter? You could generate them uniformly on the sphere, which is not very practical, or you could generate them randomly plus minus one. In all these cases, I mean, all this asymptotic, so basically these inner products become very nice very quickly, so it doesn't really matter. Yeah. Okay. Anyway, so you get this SNR, right? And okay, so now you can plug into the formulas, compute spectral efficiency and energy per bit for this scheme, and this is what you get. So as the spreading length increases, this is the performance. Sorry, decreases. This is the performance curves you get, right? So this was a big revelation to me when I started studying this, and I wanted to share this, right? That all of this, when you take the Viterbi's book and everything, right? If I understand correctly, and again, I'm sorry that this is being recorded, so I can be held liable for this, but yeah. So I think all of these old classical folks were trying to do, they were just trying to achieve the treat interference as noise curve, right? So that's what I'm trying to say. All those architectures, all these innovations, blah, blah, and so on. So this spreading gains and so all of this is just to come close to this curve, right? Of course, then, people said, wait, can't we do something smarter? Why are we doing this matched filter? Let's do some smarter multi-user detection. So there's a huge, a decade of work or so on. So like, for example, if you do MMSE decoder, then you can get closed form formulas for what the performance. And then the funny thing is that you beat a little bit treat interference as no. So you no longer have this bottleneck, right? And this architecture is still nice. So why am I keep talking about this? Because I think there is a role to be played in the IoT world, right? And for this kind of architectures. Why? Because you see, I mean, okay, so what happened in cellular networks, right? So you could see this. So this is what people before multi-user detection, right? Which is, I mean, what, late 80s, Verdu and David Shea, I mean, they all worked on this, right? So many names. I'm sorry that I shouldn't just mention this too. So, right, so they were bounded by this. Then multi-user detections came in, and now you can go up until here, and maybe with some other tricks. Actually, with some other tricks, you can even go up to here if you do successive interference cancellation tricks. So, right. But what practical folks said, they said, no, we don't want any of this. The spectrum is too precious to waste this, right? We are just going to go with the centralized planning. And that's why cellular networks work like they do today, right? They just said, okay, sure, it's a little bit more hassle, right? This poor cell phone has to all the time listen, am I allowed to speak, am I allowed to speak? Okay, now I'm allowed to speak, I can send this, right? But on the other hand, you are winning all of this, right? So this is just a fact of life. OFDM won, that's it, right? But I think, right, so it's not, we shouldn't bury all the CDMA stuff. Why? Because it has this brilliant architecture, right, where users behave in a very independent fashion. And it's very, again, I don't know, I don't have a theorem for you to say that here's how to do it to achieve good gains in IoT. But I think there is a role to play, and that's why I wanted you guys to remember this stuff and also to roughly position it in the world of these results. Okay, so this is what I wanted to say about multi-user detection and CDMA kind of solutions. Right, so I'm hoping that maybe there is some kind of comeback of this multi-user detection stuff. Oh yeah, and another thing is, okay, I'm in sort of my other life, I'm doing some mathematical research, right, and much more mathematical research, I mean, and so one exciting thing here is that actually these results depend on the fact that if you generate random signatures, then you get a random Gaussian or random Bernoulli matrix, right? And what's important for the performance of multi-user detectors is its eigenvalue distribution, right? And this is, of course, a topic of huge, interest for math folks, right? And for if you're mathematically inclined, I mean, this is why it was such an exciting thing. But all of a sudden, all those results about from random matrices, right, are actually useful for building systems. Okay, so finally, let me talk about some new problems. So let's see how well am I doing? Yeah, so about half an hour. Yeah. Okay. So right. So let's go back to the classical k-user Gaussian MAC, right? So what's the new change? So before we were thinking about few users and huge payloads, right? Okay. So now we're thinking about huge number of users and small payloads, right? So what should we do? This is one problem, right? And I mentally partition this as two separate problems. So and the second problem is random access, that we also don't want to have any coordination among users, right? That's why I was kept suggesting to rethink the CDMA type of solutions. Okay, so right, so one key metric is going to be this number of or user density. So this is okay. So this slide should be called information theory at a CT scale, right? Why? Because you see, so here's what I'm thinking. When you start, right? I mean, I'm a very numbers-driven person, right? I cannot start thinking until you give me some numbers. What's the block length? What's the typical block length? What's the typical number of bits you want to transmit, and so on. So then I had to understand how many users are actually active in one frame, and then I realized, of course, it depends on the frame size, right? If my frame is, 20,000, right? Then the number of users which want to send, the number of sensors which want to send is going to be something, right? If I double it, then twice many users will want to send here, right? It's just the law of data arrivals, right? So, okay, so then basically we need to scale, so the block length and the number of active users should scale linearly, right? There's just, it's not an arbitrary choice. It's just the interesting regime. That's it. You like it or not. That's the interesting regime. So, okay, and then you can just ask, okay, so I introduced this parameter mu, which is the speed of this growth, right? I mean, to get an estimate, if you have total number of sensors in the CT, which is k tot, and then you want to sample them, or you want them to send updates every time t sub pair, then mu will be this number. K told you, okay, so some typical number, if you take some Boston-sized city and then take some, yeah, so in the IoT world, the typical updates, like the commercial solutions, they allow you to send a few times an hour, so it's like 20 to 30 minutes between the updates. And so if you plug this in, then you get about order 10 to the minus 3. So that's the interesting user density. This was very, very pleasant to me when I noticed this. Why? Because you need finite block length information theory at exactly this narrow window of block lengths, which is about 1,000. Why? Because if your block length is smaller, you're in the regime where all bets are off, right? You just evaluate BCH versus blah, blah, right? There is nothing smart going on. If you're in the block length, which is millions, then you're essentially at capacity. You don't need this. So the only regime where it matters is about 1,000. Now, fortunately, this is the regime where, fortunately for people who do a finite block length information theory, it's exactly the regime where LTE kind of puts its frame boundaries. And also, you see, if you do, right, so each user gets about 1 over mu degrees of freedom, right? So very, very finally, right, the typical number that you would get in a CT scale is about 1,000 channel uses per user, right? So that's why I wanted to say that finite block length is going to play a lot of role in this analysis in the future. Okay, right, so let me skip this. Okay, right, so here is how I wanted to partition some of the observations here. There are 3 problems which are of separate kind. I think I'm not going to touch upon this. Actually, if I don't touch upon this, then I don't show you the main achievability result. Okay, let's see. So, right, so here's my setting, right? I have k user Gaussian MAC. Every user wants to transmit 100 bits. That's again this sort of typical number payload that this commercial solutions let you. Okay, 100 bits, right? 2 of my metrics are energy per bit and user density. Right? These are parameters which I want to trade off between each other. Okay. Wow, still reacts. Okay, so right, so as I explained, the number of users should scale linearly, right? And I explained why, because the number of, okay, so now the first work I want to emphasize is the work of Dongning Guo and 2 colleagues. So they considered the scaling for the Gaussian user, for the k user GMAC, right, in the regime when the power is fixed, P. So it turns out that in that regime, it's a somewhat, I mean, they still had to work hard, but at least you get clean numbers. So you can show that there is some capacity-like result, that the optimum per user packet, per user payload scales like this. So you can see that it explodes, right? With block length n, it explodes. So each user keeps sending a lot more and more and more, right? But the problem is that energy per bit goes to infinity. You can check this, right? Because this grows logarithmically with n, the payload size, right? But the wasted energy is n times p, right? So again, you're in the regime. Okay, so essentially this is a funny result, but I mean, if you want to sort of convince somebody from Qualcomm, right, to listen to you, this is not very relevant asymptotics. Okay, so my entire work was always on finite EBNO, finite energy per bit. Actually, before even I knew about this work. Okay, so I hope I explained to you why we need to scale linearly. Okay, so now let's go to definition of probability of error. Okay, so it turns out that if you fix finite energy per bit, right? So now, from now on, I'm only talking about this, right? So actually, for a little bit, I will be talking about infinite n. So there are lots of open, interesting questions in infinite n regime, right? Nothing finite block length in the sense of finite block length before, right? So n is going to infinity, but k grows with n. So as I said, I mean, the effective block length per user is 1 over mu, right? So in this sense, it's finite block length, but technically it's an asymptotic question. Okay, so here's the first result. The probability of successful decoding of all k messages converges to 0 for any scheme with finite energy per bit. Why? I'll show you next. But the punchline is that you need to go from from the Covert-Thomas definition of probability of error, right? As probability, you decoded everybody, to this what we call per user probability of error, right? So let me motivate it separately from what I'm going to show next. But you see, so if you are a user, you buy a subscription to Sigfox, right? This is one of the commercially available IoT solutions, long-range IoT solutions, right? And they tell you, hey, my system decodes, all the users with probability, I don't know, 0.99. Do you care? You don't care, right? What you care is how often is my message decoded, right? You don't care how often, right? Even if it's probability 1, at least some guy is incorrect. You don't care as long as your message gets decoded with probability 99%, right? So this is what this metric is, essentially, right? There's a probability that one guy's message is decoded, right? So it makes both operational sense and also motivated from the next point of view. Okay, so what's the next thing? Okay, so let's consider k users, each sending 1 bit with finite energy E over the Gmac, right, over the Gaussian MAC. You can have arbitrary n. If you want n infinity, please, by all means do. I don't care. And k is fixed here, right? K is a small number. Oh, sorry, fixed number, and n could be infinite. Okay, now you observe the sum, and then you want to decode. And what I want to say is that probability that you decode all of them decays as 1 over log k. So it goes to 0 with k. Okay, so how do you prove this? Okay, so there are several reductions. First, you see, I mean, since every guy is sending only 1 bit, right? He has 2 vectors, right? If it's 0, he sends this vector. If it's 1, he sends that vector, right? So there are 2 vectors. Okay, so without loss of generality, I mean, you can shift everything and just assume that he sends either 0 or some other vector, which we call ci, right? Okay. Okay, so here's the Gini argument. Suppose the decoder knows this vector of bits, right, up to Hamming distance 1. So just the Gini reports, right? I give you, okay, so the true message is somewhere among these k possibilities, right? Okay, so then you reduce to the following statistical problem, right? So you have observation y equals c sub u, where u is a random index from 1 to k, right? And your goal is to find k. Okay, so now this is very easy, right? Because you can do Fano and capacity calculation, right? So if you compute, I mean, the probability of decoding correctly multiplied by log k is upper bounded by the mutual information, right? Now you can ask the question, okay, with each vector here is, remember, of energy E, right? It has a fixed energy, maybe infinite length, but the energy is fixed, right? You can ask the question, okay, how much information can this system carry through, right? We don't see U, okay, but C has finite energy, so you can do capacity calculation, right? N over 2 log 1 plus E over N. Okay, so this is upper bounded by finite number, right? So you have that, right? In order to have correct decoding, this should grow logarithmically with k, but this is bounded. That's it, right? So that's the only trick. Okay, so right, so this shows us that, right? So that there is no way, even in the canonical Gaussian MAC, you can transmit with bounded energy per bit, and success rate not converging to 0. Right, so success rate converges to 0, so we have to change the definition. Same proof works for BEC. Curiously, it doesn't work for BEC. So you need to be smarter for BEC, do some induction. So anyways. Okay, so let's change gears, right? So now, okay, so now here's one upshot of this tutorial, right? That whichever problem in the classical MAC you saw, you're welcome to try to solve it with this new definition. Right? This is a new definition. I mean, it never appeared before, so you can just apply, try to go and check all the results you know. So for example, I mean, the easy thing to show is that the capacity region doesn't change with this definition for fixed k, right? Fixed k and goes to infinity, right? In the classical scaling. So surprisingly, there is no strong converse. So I wanted to show this little proof, but essentially, So, I mean, for Gaussian Mach, but for any other, I think it's also true. So what happens is, if your probability of error, if your required probability of error is slightly larger than a certain threshold, then what you can do is you can ask each user to send 0 with probability, roughly this. So then he will essentially, you reduce to k-1 user channel. And that's why, right? So even though with high probability, at least one guy sends 0, but you don't care because you're decoding per user, right? So that's the trick. So that's why there is no strong converse, so you can do some. Anyway, so actually, yeah, it took me a long time to compute, even for binary symmetric adder Mach, to compute the symmetric to compute the capacity for k equals 2. It took me some time for all epsilon, I mean. Yeah. So okay. So right. So okay. So this is one interesting problem. Okay. So now let me. Yeah. So here are the results about this, right? So now once we set this regime k equals mu n, the per user probability is given by this, right? The question is, so what can we achieve? Okay. So I proved two bounds, right? The converse and achievability bound. I mean, I phrase it in terms of the largest possible user density you can support for a given energy per bit, right? So that's how I phrase it. Okay, so there are two bounds, upper and lower bounds. This is a asymptotic question again, right? But what I'm trying to emphasize again and again, it is a misleading, right? Because per user number of degrees of freedom is bounded by 1 over mu, right? Even though it's a completely asymptotic question, I don't think we will ever compute this number exactly. So it's capacity, yeah, okay. So here is the plot, right? So this is the user density. So this is the energy per bit. Blue is the lower bound. Red is the upper bound. So the true answer is somewhere here. This is for what epsilon? This is for user sending 100 bits and 0.1 for the per user probability of error. Okay, so yeah, so the one important thing is, as I mentioned before, right? The kink happens right at the interesting regime, right? In both bounds. So remember I said 10 to the minus 3 is the order of magnitude, so that's where you are, right? So this is why it's a non-trivial setting. Okay, so now initially, when I plotted the achievability, right, and it showed this kink, I was a little bit upset. I thought my achievability is wrong, or just can be improved, right? Then I had the converse bound, which also had the kink. So now I'm kind of think that, right? So basically, what this says is the following. So here's the system kind of implication, right? Up until the user, so we live in the world where user density is this, right? So there's no users essentially, right? I mean, it's very slow, very low, right? So as the number of users increases in the optimal system, right? Again, mind you, this is right? Energy per bit shouldn't grow. So for a long, long time, until our civilization grows up to this certain scale of user densities, energy per bit consumption wouldn't grow. And only then it will start to increase, right? Now, again, this is for optimal system, if you design it carefully, right? If you do treat interference as noise, which is what current systems do, right? Why am I saying this? Because, right, the radio stations, they don't care about your IoT protocol. Sigfox protocol doesn't care about weightless protocol and so on, right? They all treat each other as interference, right? And they all operate in the same unlicensed ISM band, right? So so if you do treat interference, no, this is your trade-off. From day one, as you start to increase user density, right, you will grow like this, right? So when I saw this, I thought this is a fantastic, right? This is, I mean, I don't invent this stuff, right? This is a sales pitch by itself. Right? You don't pay information theorists, you're going to go like this. You pay information theorists, you're going to go like this. Right? That's it. So, okay, of course we don't have codes to achieve this, so this is all by random coding. But, okay, so, right, so I wanted to explain a little bit why this kink happens, but I don't have time. But essentially it's because of the, how should I phrase this? So let me explain why. Right, so, okay. First of all, this part is exactly the same thing which would hit minus 1.6 dB. Right? It's exactly the previous trade-off. Right? Because user density, you can scale it to spectral efficiency by multiplying by 100 bits. Right? You would get the same curve here, right? So why can't you ever get, you see my converse says that you cannot get there. You cannot get at -1.6 dB, right? No system can operate at that level. So why is that? Well, the reason is the following previous result that I had in my thesis yet still. So because each user is sending only 100 bits, there is fundamental lower bound, which bounds energy per bit, right? So if you just play this game, I give you 100 bits, and you have to deliver them to Mars, right? What's the energy per bit you would say, if I do optimal coding, probably -1.6 dB. Wrong. You cannot achieve -1.6 dB. To achieve -1.6 dB, you have to code over tremendously many data bits. If you're coding over 100 bits, you're just fundamentally bounded away from this. So, and this is the curve from still my thesis time, right? So this is the number of data bits, and this is how you converge to -1.6 dB, right? So if at 100 bits you're about 2 dB away, so that's what shows on that plot. Okay, so so let me skip all the mess of the research so let me just. So I said it at some point, right? That the interesting stuff starts to happen once you. So basically, what I skipped now is about 3 months of me reading papers and trying to on information theorists who try to say something about random access. All brilliant works. I mean, there are lots of open questions. But I was trying to summarize some kind of definition so I could at least start, unify this networks thinking with physical layer thinking. So this is my attempt, and I like it, and some other people like it too. So let's define the following concept, right? So we will say that a code book is a random access code for KA users if there exists a decoder which looks at their sum. Right, so these are your messages selected uniformly at random from the code book. Right, you sum them up, you contaminate it by the Gaussian noise, right, and then you give it to decoder. Well, now decoder of course cannot decode messages, right? It can only decode them up to permutation, right? Because this is notice that each user uses exactly the same code book, right? If I send blah and Krishna says 0. I cannot distinguish this from Krishna saying blah and me saying 0, right? This induces exactly the same observations, right? So that's why the decoder produces a list, right? And my probability of error is defined as probability that one, right, say wj, right, for any j, it doesn't, right, it's symmetric. So let's say w1 doesn't belong to the list, right? Okay, so this is a new game we play, right? So you have a multiple access channel. You design codes which operate as follows, right? So you have this constellation. Somebody selects a subset of this constellation, adds all these vectors, right? Produces the output vector, adds noise, and gives it to decoder. Decoder looks at this and tries to draw an original bubble, right? And his job is to have the maximal intersection with the previous with the true subset of messages, right? So this is the game we want to play. Okay, let me skip all the previous work, but the important thing is that this is actually nothing else than compressed sensing in disguise. Why? Because you see, so if you take the code book vectors, right, and stack them in a matrix, let me confusingly call it capital X, right? So these are column vectors of length n, right? Okay, so then when users select which code words to send, right, so it's like multiplying x by a ka, where ka is the number of active users, ka sparse 0, 1 vector, right? So then you observe x beta plus z. You want to decode beta, so you call it linear regression problem, right? But if you add sparsity, then somehow you change name, right, and add a couple of orders of magnitude of funding, and it becomes compressed sensing, right? So anyways, I'm just kidding. Of course, it's a deeper problem than just linear regression. Okay, anyway, so right, so then we're just in this compressed sensing. Why is it a new problem? Well, because first of all, compressed sensing folks, they don't have the concept of energy per bit. Second thing is, you see the width of my matrix. That's what in statistics is denoted by little p, right? The width of my matrix is what? Oh my God, it's 2 to the number of bits I'm sending, right? Now go talk to compressed sensing folk and if you start your conversation with saying, my matrix is of length 2 to the 100, he will shut the door, right? Right, that's it. Because all of this lasts, so all of this business, right? Coamp, osamp, boamp, whatever, right? I mean, it requires you to do operations on this, right, on this matrix. At least read it, but you cannot even read it, right, in the time scale of universe, right? That's it. So of course that's why this matrix needs to be structured in a smart way, right? And that's why you need to sort of ask Krishna. So Krishna currently holds the world record for designing these matrices. So yeah, so I think, okay, I said this, but I meant explicitly, right? Non-explicitly, I think I still hold the world record because I have random coding bound, right? So this was actually the sort of the theorem, right? So you can, I mean, I didn't say it, but you can show that aloha is an example of achievability scheme for this situation. That's, by the way, a lot of the work, which I skipped, right? This is a previous work, was guided by the following very simple question. What is aloha solving, right? I mean, if you just think about it, I hope you know what aloha is, right? You just randomly place your packet, and if it's not collided, then it's delivered, right? What is this problem that it's solving? What is this 1 over e, which is 37%, achieving? It's a fundamental limit of what, right? And so lots of people had different interpretations. That's why there's big literature, right? So for me, that also was a guiding question, right? I really wanted a definition for which aloha was an achievability. I'll bait a very suboptimal one. Okay, so here's some random coding bound. Let me skip all the proofs. Again, they're in the slides. I think this is pretty self-explanatory. So you can just check. There's some max of Gaussian processes appearing. Again, another sort of, how do you say, nugget for people who love modern math, right? So, okay, so this is the evaluation. This is the number of active users, right? And this is the energy per bit consumption, right? So this is the random coding bound, right? So as we increase, oh, by the way, the parameters also took me a few weeks to find out. So the parameters is somehow representative of this, again, communication in the ISM band across about 10 kilometers, because there is FCC regulates how much power you can blast, right? And therefore, this declares how long should the transmission be. So I mean, all of these parameters you have to figure out. But anyway, so these are representative numbers. This is what I'm trying to say, right? So currently we live in the world where there is 1 or 2 users, right, sending here, right? Very few. But as we increase density, right, we will be here. And then what does random coding bound say? Again, it's just a flipped version of that picture, is that for a long time, the energy consumption won't grow, right? And then eventually, yes. So once the number of users starts to become very large, then multiple access nature kicks in. And then you have to, okay, so, but what's more fun is, come on, yeah. Okay, so there's important, this is somehow very surprising also, but, okay, so this is what aloha achieves, right? All the standards which I showed in the soup in the beginning, right? They essentially use aloha, right? So aloha achieves this. So this is the speed of growth that you would expect with current solutions, right? So if you want, yeah, I'll wrap up, yeah. Okay, so it's sometimes, this is an old plot, yeah, where it still beats the random coding, but yeah, never mind. So yeah, nowadays they start from the same thing. So okay, so this is the treat interference as noise bound. So you can see that if we could implement CDMA type solutions, we would already be a lot better than just doing, every collision just discard kind of solution. Okay, so these are some other. So this is some CDMA with Tanaka formula. Okay, so I don't have time to show you some funny lattice-based solutions. So if you get impressed by, I mean, not if, but after you get impressed by lattices after Frank's talk, so then you can revisit these points on slides and see what our scheme is. It used to be good until Krishna beat us to death. So that, yeah, so where's the performance? I wanted to show some performance, some Berlekamp Messi. I'm skipping, yeah. So this was our performance. So this is the random coding bound, right? This is aloha, and this is what we achieved. So today Krishna achieves, I think, something like this. So like half the way from from where we were, and you can ask him how he did it. So yeah, there are many smart ideas. Okay, so thanks a lot for, I think I skipped over what, like 70% of the talk. So yeah, so my friends always joke that I prepare slides for a 6-hour talk if it's a 20-minute talk. So I think today I'm more efficient than that. All right, so I want to conclude with this slide again, right? So I hope I was trying to convince you that there are several old techniques which we need to revisit, hopefully, like the CDMA multi-user detection, which might help in the new world where we have number of users growing linearly with the block length, the new probability of error definition, and potentially also the requirement of all users using the same code book. And again, so technological sort of insight is that whenever you do, supporting many users is a hard challenge because they wake up at different times, and who knows how to do this. All right, so thank you guys for staying with me, and yeah, as I promised, I will respond to all the emails with the questions if you're interested. Yeah, thank you.